Dylan has did his maths degree in normal mathematics and applied mathematics at UCT, which after he did his honors degree in Stellenbosch. And then last year he worked at a software company in Cape Town, and now he started a new job at an agri-tech startup that was co-founded by someone he knew back from UCT. So he's currently staying in Lourens, Cape Town. And as we said before, but yeah, before the recording, yeah, he's not really started coding yet, but he's gonna code a lot, probably. So yeah, no, thank you for being here, Dylan. And yeah, you can start whenever you're ready.
I did some coding for this talk too, which I'll show you at the end. Okay, I think
cool,
I'm going to share. Let's go with the whole of the screen one, and then, yeah, there we go. This is my talk. I'm going to talk about prime numbers containing a given string of digits. And like a lot of things in my life, it was inspired by wasting time on Reddit instead of working. So in 2016, there was a thread on RMath, which asked for some surprising examples of divergent series. And for all the links on the slides, I've included a QR code in case you want to follow it on your phone, and you don't have to type in the web address down there. And the two examples that came up, in one of them he considered a set of prime numbers with a prime number of digits, and it turns out that the sum of the reciprocals of these things diverges. So a lot of people already know that the sum of the reciprocals of the prime numbers themselves diverge, but even seemingly very small subsets of the prime numbers are still common enough that the series diverges. And the other example that was also surprising in the same post was if you consider all the positive integers that don't have a 9 anywhere in their decimal expansion, but they're allowed to have any other digit, then the sum of the reciprocals of these things converges. And these were surprising because it feels like there should be a lot of these numbers without a 9 and very few prime numbers, and the opposite's true. There's enough prime numbers that their reciprocals diverge, but not enough of these 9-less numbers that their reciprocals converge. And at the same time, I realized that if you combine some appropriate generalizations of these two claims, you can come to the conclusion that there are infinitely many prime numbers which have a prime number of digits and which contain any given string of decimal digits that you like. And so, of course, I promptly told everyone I know. I even wrote a blog post about it. So a bit about this blog. It's not my blog. It was started by, among other people, but I became aware of it from a lecturer at UCT. And his idea was that it's a sort of collaborative blog where a number of students and professors and a whole bunch of people have login details and can write articles for the blog. And it's sort of a collaborative picture of mathematics, ostensibly mathematics from an African perspective, but mathematics is mathematics, but it does focus a lot on what is going on in South Africa and Africa in general, conferences and talks and that sort of thing. But it's a good mathematics blog. I don't know how active it is anymore because this was 10 years ago and I'm old now, but I do still plan to write some content for it later on. And so in this talk, I'm going to follow the argument presented in the blog post, but it turns out that by considering convergent and divergent series, that's like needlessly complicated a way to prove the thing that I claimed was interesting, that there's prime numbers with any digits you like. Let's make this full screen. That's better. It turns out you can prove that a lot more directly without going through series, still using you don't actually even need the prime number theorem in its full power. I'll mention that at the end, I think. So at the end, I will prove instead that for any given string of digits, there's a prime that starts with that string with every number of digits that you care about. So it's not even special that it's primes with a prime number of digits. It's there's such a prime with 1,000,000 digits and 1,000,001 digits and 1,000,002 digits. It's literally with any number of digits you care about. So there's lots of primes, and I'll talk about that, like I said, towards the end. So the first example that a lot of people come across of a series that diverges is the harmonic series. It's sort of well, it's not the simplest example. The obvious things that diverge is just, 1 plus 2 plus 3 plus 4 plus 5 is infinity. Don't let anyone tell you otherwise. They are lying to you. It's not -1/12, it's infinity. But the harmonic series is the first sort of surprising example because these terms are getting smaller. They're just not getting smaller rapidly enough that this thing has a finite sum. So I've written out a sort of proof over here, but it's difficult to follow mathematics. But the basic idea is that you sort of group these things in blocks of powers of 2. So it turns out that the 1 at the start is at least 1. Then you have a half, which is a half. Then you have a third and a quarter. And both a third and a quarter are at least a quarter. So when you add them in, you get at least 2 quarters, which is a half. And the same for a fifth, a sixth, a seventh, and an eighth. Each one of those is at least an eighth, and there's 4 of them, so you're adding at least another half. And in a ninth, a tenth, up to a 16th, all of those are at least a 16th. So when you add, and there's 8 of them, so when you add them in, you get another half. So it's 1 half, a third, plus a quarter, plus a fifth, plus up to an eighth, plus, this is what I was saying, plus up to a 16th. And there's a reason I'm going through this, because I'm going to use a similar idea, but in the other way, to prove that the other series converges. So these, I said, are each greater than or equal to a quarter. And these 4, so that's greater than or equal to 4/8, because each of them is at least an eighth. And then these 8 numbers are each, there's 8 of them, and they're each greater than or equal to a 16th. And so this thing in general is bigger than a half, plus a 1, plus a half, plus a half, plus a half, and so on. And that obviously gets larger the more terms that you add. And so the harmonic series is an example of a series that diverges. Now, if we go in the opposite direction, okay, so I said we of course get different behavior if instead of summing the reciprocals of all of the natural numbers, we only consider some subset. So for example, powers of 2, there's few of them that this converges. This is converges to 2. Reciprocals of the prime numbers diverges. And I mentioned earlier that if you considered numbers that do not have a 9, that converges. And like I said earlier, that's at least a little bit surprising because it feels the wrong way around. It feels like there should be lots of numbers without a 9. So I'm not going to consider just the 9. I'm going to consider any string of digits you like. So we're going to consider the set of natural numbers and we're going to consider the sum of those natural numbers that don't contain that digit, the sum of the reciprocals of those natural numbers. And the approach that we will take to show that this converges is similar to the one that we used to show that the harmonic series diverges. Here we group them in blocks of powers of 10. And instead of taking that each one's bigger than the smallest element in the block, we go with each one is smaller than the biggest element in the block. So we're going to use that to bound this above. So we get that if m is the length of S, we group together the numbers between m plus 1 digits and k plus 1 m digits for some k. So it's numbers with 1 up to m digits, then m up to 2m digits, then 2m up to 3m digits. And this is what you get. You get that this thing is equal to the sum over all of the blocks. And then it's the sum of the numbers in each block that don't contain S. And we're considering the reciprocals. And each of these numbers in this block, each n is bigger than 10 to the km. So their reciprocals is less than or equal to 1 over 10 to the km. So we replace each number in this block with the largest number in the block. And to turn this into a bound that's useful, so we want to know how many of these are we summing. So earlier we saw that we had 4/8 and then 8/16 and then 16/32 and 32/64. So in this case, our question is how many 1 over 10 to the km's do we have? So we want to get some handle on how many such numbers are there. How many? And one way to do this is we consider such a number. And so here's our number. It's got a digit, a digit, a digit, and it's got a whole bunch of digits. And what we're going to do is we're going to look at groups of digits that have the same length as S. So this has got length S, length S, length S. And in each of these, this block of digits on its own can be anything you like except for S. So there's m digits in this block. So there's 10 to the n options for what this block is, because there's 10 options for each digit, minus 1 because we have to exclude S itself, because we want the number overall not to contain S in its digits. So I've written this out here. It's break the digits of n up into k plus 1 consecutive blocks of m digits. One of the blocks might have to have fewer than m digits if the number of digits is not a multiple of m, or you can think of it as adding leading zeros to the number if you prefer. And so, as I said, there's 10 to the n possible blocks of m digits. Each block can be any one of these possibilities except for S. And so there's 10 to the m minus 1 to the power of k plus 1 possible, at most this many. So every number that we are considering has to have this pattern. But we also, you want to be stricter. These overlaps are not allowed to, this group of digits there is also not allowed to be S. So actually it's like a lot smaller than this, but it turns out that this upper bound is good enough. And so we get that the sum of the numbers that we're interested in, those natural numbers that do not contain S in their decimal expansion, is less than or equal to, this is the number of elements in the block, and this is the largest element in the block, and so we get that it's less than this thing. But this, as you'll notice, is it's going to be a bit awkward to circle the part I actually want, but this in general looks like this to the power of k times something. In other words, it's a geometric series, and because this common ratio is less than 1, this geometric series converges. And so, in fact, it converges to 10 to the m times 10 to the m minus 1. And so that's how we can prove that these numbers, without, say, for example, your phone number in their digits, that their reciprocals converge. So now I'm going to look instead at the series that involve the prime numbers. So in his talk last week on the 1st of April, Lourens introduced the prime number theorem. Well, I suppose, Legendre introduced the prime number theorem, and the Villers-Poisson and Ademar and Gauss and everyone else that considered it introduced it, strictly speaking, but Lourens spoke about it. And the prime number theorem says that if pi of x is the number of prime numbers less than or equal to the real number x, then asymptotically pi of x is x over ln x. In other words, the limit of pi of x divided by x over ln x equals 1. And formally what that means, at least when you do real analysis, I think in second year, you'll learn what it means for what this limit means. It means that for all large enough n, or for all large enough x, for any epsilon you care about, for all large enough x, this is true. And in this talk, I'm actually only ever going to use the case of epsilon equals a half. So strictly speaking, I'm not using the prime number theorem. I'm using a weaker form of a special case of the prime number theorem. I don't actually need the full power of the prime number theorem for anything I'm going to talk about in this talk, but it is still prime number theorem-like result that will be used. One of the consequences of this, and I do have slides that goes through a sketch of a proof, but I don't think there'll be time to go through them in like any sensible amount of detail, is that the nth prime number is approximately n times log n. And the way to get it from the prime number theorem is that if we consider the ratio of the nth prime over n log n, this is the same thing as basically if we plug the important thing to realize is that pi of Pn, the number of primes smaller than or equal to the nth prime, is n by definition. There's n primes that are at most the nth prime. And so if you plug that into the prime number theorem, you get that this thing over here, Pn over log Pn divided by pi of Pn, goes to 1. So this claim that I'm making over here is actually the claim that this limit over here is 1, which is not completely obvious, but there are ways to prove it. I've got some, so I've said here that it's possible to show that this is 1. It is indeed possible. There's like a sketch over the next. In fact, even in my sketch, I said I'm going to leave out this part. If you ask me nicely, I'll prove that. There's and I'm very happy to prove that because there's a very nice, simple proof of that. But as you can see, there's a couple of pages of stuff here to justify that limit. But the end result is that this is in fact 1. So this part is 1. This part is 1, which means that Pn is asymptotically n log n. And so there's a lot of things that you can do with this. I'm going to use it first to show that the sum of the reciprocals of the prime numbers diverges. There's a lot of simpler proofs, but if you're happy to accept the prime number theorem, then this is by far the shortest proof you'll be able, well, short if you ignore how long the proof of the prime number theorem is, but the fewest slides that I can take up to prove that this is true. So if we're willing to use the prime number theorem, then the limit comparison test tells us that the sum of the reciprocals of the prime numbers converges if and only if this sum does, because this is because limit of 1 over n log n over 1 over Pn is 1. In turn, this sum, it's like a decreasing function. It meets all sorts of conditions that are necessary, but I'm not going to talk about all the conditions it has to satisfy. It converges if and only if the corresponding integral converges. Replace the n log n with x log x and integrate. And this integral you can do with a substitution. If you let u equal ln x, then du is 1 over x dx. And then this integral is the integral of u du from appropriate point to infinity. And ln 2, I think, with the bounds that I used. And you get that this integral is,
You mean 1 over u, right? That integral.
Yeah, sorry, 1 over u du. Thank you. And 1 over u du is, ln abs u plus a constant. So I've got here that this integral is then log of log x, and that grows very slowly, but it does diverge. So this integral diverges. So the sum of 1 over n log n diverges. So the sum of 1 over the prime numbers diverges. It's using, it's using a nuclear warhead to swat a fly, because the prime number theorem is a very complicated result, while the fact that the primes diverge is somewhat less complicated. But that's okay. At least you'll believe me that they diverge. So a generalization, we're going to consider primes of a prime number of digits, and there's enough of those that sum also diverges. And in fact, even more generally, primes of a prime number of digits, and where that number of digits is itself a prime with a prime number of digits, and keep going. So let S0 be the set of natural numbers, and for each n, let Sn be the set of prime numbers where the number of digits in the decimal expansion is in Sn minus 1. So primes of a prime number of digits, and where that number of digits is a prime with a prime number of digits, and where that number of digits is a prime with a prime number of digits, and so on as far as you like. And the sum of that still diverges, which is slightly more surprising. And in particular, the fact that if you take S2 in this notation I've used here, in particular because it diverges is infinitely many, because any finite sum converges. We'll prove this by induction on n. N equals 1. No, that's a lie. It's for n equals 0. We just have the harmonic series. And we saw that diverges. I'm going to have to fix it on all of these slides. That should be a 0. The claim is that the harmonic series diverges. And now let's suppose that we've established that the sum of the reciprocals of the primes in one of these special sets diverges, and we consider the next set. And our usual trick, we break it up according to the number of digits. So k here is number of digits. And then we replace the elements in each block with the smallest element in that block. So in this is smallest in the block, and this is the number of terms in the block. So the same way we did with the harmonic series, the same way we did with the series of numbers missing a certain string of digits in the decimal expansion. Break it up by number of digits, and then each block replace it by the smallest one. And then the question, then once again, we need a handle on how large is this set of primes that's in PK and S. Yeah, the set of primes with K digits, where K is one of these things in Sn. So by definition, the primes that we're summing, if it's in Sn plus 1, the number of digits is in Sn. So that's why number of digits is in Sn by definition of Sn plus 1. And so yeah, how many primes are there with K digits? If all we're interested in is knowing that this diverges, since we know that the harmonic series diverges, since we know that some K in Sn of 1 over K diverges by the induction hypothesis, it's enough to show that this thing is in fact just bounded below by something over K, because then it's bounded below by something times this sum over here, and C, it should be positive constant C, because if you can obviously show it's greater than or equal to 0, but that doesn't tell you anything. So if there's some positive constant C such that this is always true, then that establishes that this also diverges because this does. And this only has to be true for all large enough K, because series only diverge or converge based on their long-term behavior. You can ignore the first as many terms as you like. So as promised, I only ever use the epsilon equals a half case of the prime number theorem. So there's some natural number n such that whenever m is bigger than that, so whenever m is large enough, this is true. So in particular, if k is large enough that we can use this bound for m equals, so we use this as our value of m, assuming k is large enough. Then we know that pi of 10 to the k minus 1, we use the upper bound, we get the 3 over 2 times this thing. And pi of 10 to the k is we use the lower bound, it's greater than this. And we have that the number of primes with k digits is pi of 10 to the k minus pi of 10 to the k minus 1. So this is the number of primes of at most that's at most 10 to the k. This is the number of primes that's at most 10 to the k minus 1. And all the numbers in between those two have, they precisely the numbers with k digits. And also, I've sort of like implicitly used the fact here that 10 to the k itself is never prime, because otherwise I'd be including a prime with k plus 1 digits. And the same thing here, I've implicitly used the fact that 10 to the k minus 1 is never a prime, because otherwise I would have excluded a prime that I should have included. But that's like a slight nitpick, but these numbers are never prime. Well, yeah, never prime. So in this case, now we use these bounds that we had. We can, because this is greater than this, it means that minus this is greater than minus this. So that's how we get that part. That 3 over 2 comes in there, and we have the upper bound over here, and you manipulate this and you end up with this thing that looks a lot like k over k squared, which looks a lot like k, and if you're careful you can choose k so that this is in fact it's not, I don't want to go through the details, it's not a lot of details, but you do in fact get that this is bigger than c over k for all large enough k, which is what we're actually interested in. So yeah, putting it all together. So let S be some string of decimal digits, any string you like, As before, we consider the set of primes where the number of digits is prime, number of digits and number of digits is prime, and so on. We consider the set of natural numbers that contain S somewhere in their decimal expansion, and suppose that there's that this is finite, that there's only finitely many natural numbers that have S somewhere in their decimal expansion that's also one of these special primes. And that means that from some point onwards, every prime in Sn is not in NS. This is nums with S in digits. I've written it up here, but like just to emphasize it. So if there's only finitely many of these special primes with S in their digits, then from some point onwards, every one of these special primes does not have S in its digits. So it follows that if we take the reciprocals of those primes, of these special primes, every single one of these, all of these, don't, from some point onwards, don't have S. So every term in this sum is a term in this sum, because this sum is over these special primes, and this sum is over the terms that don't have S in their digits. And we assume this is finite, which means that from some point onwards, every one of these primes is one of these numbers. Every term here occurs here. But this is a contradiction because we already saw that this thing diverges while this thing over here converges. And so there are, in fact, infinitely many primes of any given string of digits you like that also have a prime number of digits, and where the number of digits is a prime that has a prime number of digits. And I'm getting tired of saying prime, but you can keep going down as far as you like. I mentioned at the start that going via convergent series in this way and divergent series is a bit less direct than what is possible. In fact, like I said, there's a prime number with any number of digits you care about, that you can even assume that it starts with your set of digits. And this implies also that S can be anywhere in the prime that you like, because you can append digits. So if I wanted a prime that has 1, 2, 3, 4, 5 in it, and I wanted the 1, 2, 3, 4, 5 to appear in position 7, I can just add 7 random digits, 1, 2, 3, 4, 5, and the theorem still tells me that there's infinitely many primes that start with 7 random digits, 1, 2, 3, 4, 5, and so on. So this also is a consequence of the prime number theorem. Again, I've said, yeah, this shows that having a prime number of digits isn't special. There's an appropriate prime number with almost every number of digits you care about. And so let M be so instead of talking about this string of digits, and I've always said string of digits instead of number because I want to allow for the possibility that the string of digits you care about starts with a 0. But if I'm going to talk about it being at the start of the number, then I don't want to allow leading zeros, because then typically the convention is that you don't write leading zeros when you write down your number. So I've said let M be the natural number whose decimal representation is S. Now we're actually thinking of S as a number. And if S starts with a 0, instead let it be the natural number whose decimal representation is 1 followed by S. So that this number, so that the 0 does actually show up in the digits we're considering. We want to show that for large enough natural number n, there's a prime between 10 to the k m and 10 to the k plus 1 m minus 1. In other words, with k plus m digits. Why have I used k? I've said here n and here I've used k. So the simplest way to fix that should be a k for that line to make sense. So equivalently, now I've gone back to using n. So now the simplest fix is for these to be n's. Equivalently, we want to show that the number of primes that's at most 10 to the n plus 1 m minus 1 minus the number of primes that's at most 10 to the n m minus 1 is positive. So there's at least one prime in between these two numbers for all large enough n. And here I've been more careful. I mentioned earlier that strictly this is the number of primes in that range, but it's much easier to work with these numbers instead of having the -1s in it. And so since 10 to the n m is never prime, this thing is actually equal to this thing, and this thing is equal to this thing. And the reason that's more convenient is because then 10 to the n m I can write as n ln 10 plus ln m, whereas this thing I'd have to then go in, I'd have to add x. Yeah, it would just be awkward, a bit more awkward to deal with. This is just slightly more pleasant. So again, the epsilon equals a half case of the prime number theorem, or in that epsilon delta definition of what the limit in the prime number theorem means. I know that for large enough x, this is true. So for large enough x, like we did earlier, this means that pi of this minus pi of this is at least this. So we want to show that this is, we want to show that this is positive for large n. And since this thing, which is what if you were to write this over a common denominator, you'd have this divided by this. So this is equal to dot divided by square. No, actually, it's equal to dot times square. Whatever. It's this part of what you get is positive. And so we actually just want to show that this is positive, which is once you take the 10 to the n m out of here, you're left with a 10. So you want to show 10 ln 10 to the n m minus this is positive for large n. But it's equal to 7n ln 10 plus 7 ln m minus 3 ln 10. And in fact, this thing that we have over here turns out to be always positive, because the 7n is bigger than 3. So you've got something that's bigger than 3 ln 10 minus 3 ln 10 plus another 7 ln m. So this is huge. This is very definitely always positive. So the restriction on how large n has to be doesn't come from this part of the calculation. It comes from n needing to be large enough that this bound actually applies. And so I've written here that it follows that as long as n is large enough, that 10 to the n, I probably mean 10 to the n m. So I actually mean 10 to the n m, not 10 to the m, satisfies this bound. Then we have that there's a prime with n plus length s, possibly plus 1 digits, that either starts with s or with 1 followed by s. And so all the everything else, if this was the part that if this was the result you were interested in proving, everything else in the talk was a distraction. But the fact that those numbers, the reciprocals of those numbers diverge, is an interesting result in its own right. And just knowing that this claim over here, exactly as written, is true, doesn't tell you that the sum of the reciprocals of those numbers diverges. So those are actually two different results, and depending on which one you're interested in, either the first half was a waste of time or the second half was a waste of time. So hopefully there are sufficiently many people that were interested in at least one of the two, or found at least one of the two interesting. So yeah, then I've added a question here that we actually need the prime number theorem. So other than when showing that the reciprocals of the primes diverges, they are actually used. I might not have needed to, but I did. I used the prime number theorem in its entirety. But everywhere else, when I've invoked the prime number theorem, this is actually all that I needed to use. And in fact, even weaker bounds would probably have been sufficient. So I mean, I didn't actually have to use a half and 3/2. No, I probably could have gotten away with this being even as small as 1/10 in some cases, and this being, correspondingly larger, 11/10. And for some of these weaker bounds, there are much more elementary proofs that are known. So I saw someone claim online, but I didn't look through it, and it was probably, yeah. They claim that you can show that 1 over 6 x over, let's use n over ln n is less than pi of n is less than 6n. They claim that this is possible to show by considering the primes that divide this binomial coefficient and then using the fact that this is bigger than, less than 4 to the n and bigger than, I think, 4 to the n over n plus 1. Some kind of bound like that, and then considering the primes that has to divide this thing. The claim was that that is sufficient to establish a bound of this type, in which case you don't need analysis and you don't need Tauberian theorems and you don't need zeta functions and poles and analytic continuations and who knows what else. Apparently there are much more elementary proofs known for the sort of prime number theorem-like results that I actually needed for the things I spoke about today. So perhaps they can be explored in an upcoming talk. It's prime time infinity, elementary proofs of prime number theorem-like results. Probably not. I don't know if that's a talk I'd be that excited to give, but yeah, I could. They also happen to show up in the honors course in analytic number theory, unless I'm now so old that the course has changed significantly since I, took it, or just doesn't exist anymore. I don't know. It's been a while. Honors was actually like 5 years ago, which is scary. And yeah, I mentioned that I wrote some code for this talk. So I took some time to implement the Bailey PSW pseudo-primality test in my favorite language in the world, not really, JavaScript. And this allowed me to create a site where you can enter a string of digits and it will find up to 1. I cut it off at 100. It could find all of them if you wanted it to. But then it's going to start using up lots of resources and take a lot of time and so on. But up to 100 prime numbers with a given number of digits containing the given string of digits. And you can try it out here. There's a link in the slides and there's a QR code if you want to use it on your phone. And this is what it looks like. It's not the prettiest design, but let's say I wanted to find a 13-digit prime number containing my phone number, which happens to be 01234567889. You can see I already tested this thoroughly. That's why. And I click go, and it will list out the numbers. And it even kindly informs me that there were actually more than 100, but that it's only going to show the first 10 pages of results. And you can use this as a prime test of sorts if you wanted. So if I wanted to know, is the number 3141 prime, I can say find prime numbers with 4 digits containing this string that just happens to be 4 digits long. And if this is amongst the results, it won't be because it's divisible by 3. So if this is amongst the results, then it must be prime. And if this is not amongst the results, then it wasn't prime. So it's not because it's not prime. Is this number also not prime? 5 will definitely not be prime. 7, wow, okay, 9. 5, 1. 5, 7. There must be a prime somewhere around here. Okay, 2017 was a known prime number, and it correctly tells you that 2017 is a prime. And I can't remember how many digits of pi it was that was the first that many digits happens to be a prime number. 5, 3, 5, 8, 9, 7 probably. 2, 3. A 14-digit number, and no, 13-digit version. 12, 11, and 9. I don't know, but you can play with it. It is there, and it will always be there because it's it's not. I'm not hosting it. It's hosted on GitHub pages, and yeah, that is That is my talk. I don't know if there are any questions or comments or anything else. But hopefully it was somewhat interesting.